and this will be online lecture, which is lecture 9. In this lecture, we will derive the Euler Lagrange equations, Noether symmetry equation, and the corresponding conservation laws. Outlines of these lectures are introduction, Euler Lagrange equation and conservation laws, Noether symmetry equation, examples and references. We see that Euler Lagrange equations are dynamical equations, and it corresponds to an action. Action is an integral over the Lagrangian density. Define a Lagrangian for the dynamical system and integrate over the given space-time will give us an action, and we derived Euler Lagrange equation from that action, the variation of that action. So basically in this talk we will derive a Lagrange equation, conservation laws, and Noether symmetry equation. Noether symmetry is connected with the conservation law. For each Noether symmetry there is a conservation law. It is the famous theorem of Noether, and is very important in mathematical physics and applied mathematics. Nowadays it is used in cosmology and other sciences to define conservation laws for the given dynamics. So let's start. The action is given in 2.1. It is a function of the dependent variable phi, independent variable x, and the derivative of the dependent variables. Its optimal value is called action. It is integrated over the given region, over the given space, or over the given space time. So we will do this for this. We will take this action for the space-time coordinates. Noether use this type of variation in his work. Variation is in the independent variable, variation in the dependent variable, and variation in the derivative of the dependent variable. The corresponding variation in the action will take this form, which is given in 2.3. This is the new coordinate and this is the old coordinate. So the difference between these two will give me the variation in the action. More elaborately, the actual Lagrangian plus variation in the Lagrangian will give me the new Lagrangian. And this term is come due to the change in the independent variable. So subtracting them, we will get these two terms only. We get 4 term from here, but we will neglect the term in which two variation multiplied, this one and this one. So multiply this one with this one, we will get a term, but we will neglect that because two variation multiplied in that term. We take the variation so small that the two variation will be neglected. Okay. Now subtracting this term from the above, we get this one, this equation. Okay, now this is the variation in the Lagrangian. The variation in the Lagrangian occur due to their variable. x phi and the derivative of phi. So this is variation in the Lagrangian due to phi. This is the variation in the Lagrangian due to the derivative of the phi, and this is the variation in the Lagrangian due to the independent variable x, and this last term is the same, this one. Okay, now you see these two terms can be put in one, the derivative of the product of L and delta x. So this is the same equation 2.6, but we put two term in one. Now using this identity, these two operator commute. Variation in the dependent variable, delta naught is variation in the dependent variable keeping x constant, and partial mu is the total differential operator. These two operator commute, so we need to commute these operator to get this term. Now this term can be put in these two. You see this is the product of this one and this one, so differentiating the first one leaving the second will cancel this one, and differentiating the second one leaving the first one is this. So the net outcome of these two term is this middle term. Why we did it? We did it for some purpose, and that purpose is to take this delta naught phi common from these two to get Euler Lagrange equation. These are Euler Lagrange equations, and to put these two in one bracket is to take the total derivative common, so that is common, and put this into the bracket. So now if I take optimal value of the action, the variation of the action will be 0. So taking the variation 0 for optimal value of the action, this integral is 0. This integral is 0. This integral is 0 mean the integrand is 0 because we take r arbitrary, variation arbitrary. So we get this equation putting the integrand equal to 0. Now we know that these are Euler Lagrange equations, so putting them equal to 0 if it is satisfied, if they are satisfied, if it is 0 and it always 0, so in that case I will left with this thing, the derivative of this thing to be 0, this one. So what this equation tell me? This equation tell me that the total derivative of something inside the bracket is 0. That mean the quantity inside the bracket is not changing under the total derivative operator. That means that is a constant for the total derivative operator. So when you integrate it, you will get a constant. That means it is a constant. That means it is not a constant, but it is a conservation law. Is constant for the total differential operator. So this is my conservation law for my purpose, but generally the variation in the action is not 0, but it is equal to some divergent term. So putting this divergent term over here in equation 210, we get this information that the integrand will be this thing, the whole this one up to here is the previous one minus the total derivative of a equal to 0. I put it on this side. So, oh yeah. What this mean? This mean that I can write this equation in this form. Now, if Euler Lagrange equation satisfy this quantity is 0, this is 0, so I left with this quantity, the derivative of this quantity is 0. That means whatever is inside this bracket is constant, and that is the more general form of the conservation law, not most, because we are taking only the four vectors. Space-time coordinates, which is 4. More general case will be the case in which we take more independent and more dependent variables. I mean, let's say n independent and m dependent variables. So anyhow, for our case, this is the conservation law. This is the conservation law. See it, whatever is here. But this is not the well-known form. We have to change a little bit this one using this equation. Oh, what is this? This is a variation. This is variation in the dependent variable keeping x constant. This is variation in the dependent variable allowing x vary. So allowing x vary, we have to subtract this term. So put this identity into the previous equation, this one over here. We get this equation. This is the conservation law, new form of the conservation law, but it is also not very well known. What is delta phi? Delta phi is eta I. Delta phi I is eta I. It is given in the Noether variation equation given in the start. We will see it again. This is xi. Xi is gauge function. Let's see it again. Variation in phi is eta I. Yeah. Variation in x is xi. Variation in phi is eta I. And variation in the derivative of phi I is the derivative of phi I. This is the well-known form of the conservation law. This is the well-known form. The well-known form of the conservation law is 2.20. Okay. Now let's see the Noether symmetry equation. Where the Noether symmetry equation come from? It is from the same action. From the equation we derived the Euler Lagrange equation and the conservation law. That is from the 2.6 equation. Let's see 2.6 again. This is 2.6, you see, and I write this equation again. This one. This is the same 2.6 equation. Now this is 0 because this is 0, so the integrand is 0 because we take R arbitrary, the region of integration arbitrary. So we get this equation. The integrand is 0, and the integrand equal to 0 is in fact the Noether equation with a little bit modification. What we modify we modify this thing. We will put this as eta I. This is eta I mu. We will first interchange these operator. Change these operator. This is delta mu delta naught pi I. So that delta naught pi I is eta I, and the derivative of pi I with respect to mu is pi I mu. So this is eta I mu. This is eta I. This term come from here. Total derivative operator on L and x mu is xi. So these three terms are these three terms. The first one is from here. This one is the first one. The second one is this one, and the third one is this one. And this is the same, this term, and that is the same. Now we see that L is common in these three terms. So take out that common. What is the inside? The inside is the first prolongation of the Noether symmetry generator. So I put hole inside the bracket is x1. Operate on L. L total derivative operator on xi and total derivative operator on A. This is the more compact form of the Noether symmetry equations, and this equation is very famous and used in mathematical physics frequently, and also other branches of sciences. Nowadays it is used in cosmology as well. So this is another equation. So far we derived Euler Lagrange equation, conservation law, and Noether symmetry equation, and all of them are deeply connected with the action for the dynamical system. Okay, so let's see example 1. I take this Lagrangian, space-time Lagrangian. This is 4-dimensional Lagrangian, first order. Their Euler Lagrange equation are given over here. How these are derived? These are derived. Let's decide first what are the independent and dependent variable in this Lagrangian. The dependent variable are t, x, y, and z, and the independent variable is s naught, not s naught, s arc length parameter. This t naught is the derivative. This is dt by ds, the derivative of t with respect to the arc length parameter. So the dot is due to the arc length parameter. So the arc length parameter is independent variable. T, x, y, and z are the dependent variable. So we have 4 dependent variable. We need 4 Euler Lagrange equations. So they are 4 in number: 1, 2, 3, and 4. Let talk about how they are derived. It is derived from the Lagrange equation given somewhere in this 2.16. These are Lagrange equation. This is partial by, so let's say part t is dependent variable, so this is partial L by partial t. This is d by dt partial L over partial t naught equal to 0. So for This term for t is this is 0 because in my Lagrangian there is no t. In my log is independent of t. So the first term is 0 and the second term will give 2 time this 2 time 2 time it is equal to why this is constant because there is a d by dt term. This is d by dt. I this is 2 time x over alpha a t naught, and d by dt this term is 0 equal to 0. So integrating this with respect to time, I will get a constant c1 here. So that is this one. Similarly the other one, you can use that equation, and student should calculate these four Euler Lagrange equations. What are Noether symmetries? So these are Noether symmetries. These Noether symmetries are in fact come from the Noether equation. This one, this 3.6 equation. No need to calculate these symmetries, but taking these symmetries, calculate these conservation laws using equation 220. Using this equation and taking these symmetries, Noether symmetries, find out all these conservation laws. Phi naught is corresponding to x naught, phi 1 is corresponding to x1, phi 2 is corresponding to x2, and so on. So take these Noether symmetries and put them into the conservation law expression given in 2.20. Similarly, this is another example. This example I only change, this is 2 in the previous one, so I take it a general. These are the Euler Lagrange equations. You can use the previous Euler Lagrange equation which is given in 2.16 and derive these. This is homework. All the students are advised to, as a homework, do this work, derive these Euler Lagrange equation, and using these Noether symmetries derive these conservation laws. These are six. Let's see. I think this Lagrangian admits 8 symmetries, but only six are given. But doesn't matter. Find Noether charge or conservation laws corresponding to only these six Noether symmetries using expression 2.20. So your homework is to find these conservation laws using these Noether symmetries in the second example and in the first as well. And that's all about this talk, I think. And these are the references you can consult for your concept, to strengthen your concept. Use these examples. I think the Blumen in Komai book, I think, is available on net. Is a very theoretically very strong book, and you can consult it and you strengthen your um, concept about conservation laws and Euler Lagrange equation. Similarly, this one is very easy to understand, is also available online. So all these books are very important, and your Analytical dynamics and the portion of Euler Lagrange equations in conservation laws can be understood using these books. Thank you. Allah Hafiz. Take care.